As now, it is my pleasure to introduce the Sierra Fund's Science Director, Dr. Carrie Monahan. Dr. Monahan leads our Center for Collaborative Science around watershed reclamation. Her impressive resume in our program doesn't begin to describe how proud we are to have Dr. Monahan as the principal scientist overseeing our research at Malakoff-Diggins State Historic Park. That data that's coming out of that research is proving to be extraordinarily valuable to demonstrate that indeed these legacy hydraulic mines do contribute ongoing levels of mercury in the delta and the river systems. I'm personally very grateful that that work has happened. Additionally, she works in the Combi Reservoir in cooperation with the Nevada Irrigation District in one of the most important pilot reclamation projects for removing mercury from sediments. In our project cooperation, and additionally, we have a cooperative project with Nevada City to evaluate for possible acquisition the site of the old Champion and Providence mines.
Thank you so much, Gary. That was really kind of you. It's so great to see you all here, and I really want to thank you all for your participation. Your time in coming down here means so very much to us. It's my pleasure to introduce our very first speaker. This is Dr. Singer. He's from the University of St. Andrews in Scotland. His talk is entitled Enduring Legacy of a Toxic Fan via Episodic Redistribution of California Gold Mining Debris. We had hoped to bring him here from Scotland directly, but unfortunately, we haven't been able to do so. So we're Skyping him in from the UK. We can do this. Dr. Singer earned a Ph.D. from the Donald Bren School of Environmental Science and Management at the University of California, Santa Barbara. Singer is a lecturer at the University of St. Andrews and a researcher for the Earth Research Institute at UC Santa Barbara. His work has focused on hydrologic and geomorphic aspects of environmental problems, including the legacy of the 19th century hydraulic gold mining in California. In recent work, Singer has led a team of investigators on a study of mercury contamination and bioaccumulation within the food web of California's Central Valley. Dr. Singer, can you hear us?
I can hear you. Can you hear me?
We can. Welcome to California.
Great. Thank you very much. Should I start?
Yes, please.
All right. Thank you very much, Carrie, and thanks for the invite to speak to you all today. I really appreciate it. I realize it's quite unusual to be so remote, but hopefully I have an interesting story that will make it worth it, the remote presentation. So this story actually doesn't start in the Sierra Nevada. It starts in the Sacramento Valley, where I had been doing some work coring sediments to try to figure out how quickly floodplains were filling up with sediment. So I was out there with Ph.D. students coring into floodplains, and then we would take the cores back and date them using a dating method. And one day we came across a sign that said sand, and we thought, that's very strange, because there really isn't any sand around here. All we see around us is clay and loamy soils that are suitable for rice farming. So we followed the signs, and we came across something very surprising. It was a massive deposit of sand that was several kilometers in width and in length, covered a really large area. And when we inquired further with the local farmer and we did some measurements, we determined that there was about 2.5 million cubic meters of sediment that arrived during a single flood in 1986. And it completely buried a farm, a rice farm in the Sutter Bypass along the margins of the Feather River. And I thought to myself, where could you possibly get that much sand to move during a single flood? And I immediately thought of some work by a colleague of mine, Alan James, who had been working up in the Sierra Nevada on the legacy of gold mining. And I wondered, could it be that the sediment comes from there? Well, just a bit of background here. Most people, when they hear the term gold rush, they think of this. They see an old grizzled miner with a long beard sitting alone in a stream bed and mining for gold with a pan, all alone. And but as you've already heard a bit, this is sort of just a romantic notion of the California gold rush. for the real gold rush in California was really driven by engineers. Notice these guys don't have beards, these guys sitting on this hydraulic monitor. They're wearing hats and wearing ties and nice shoes. These are engineers who developed an industrial process to extract gold from the hills. So with the invention of the hydraulic monitor in 1852, and for the subsequent 30-odd years, there was an industrial process of hydraulic gold mining that totally reshaped the foothills of the Sierra Nevada. And a lot of that mining was actually concentrated within the Yuba Basin, which I'll feature within this talk. So essentially, the hydraulic monitors would shoot high-pressure water at hillsides, bringing down all of the sediment that they contained, including the gravels that contain the gold. And that sediment would be run through these giant sluices like you see here, where the gold would be extracted. And all told, about 1.1 billion cubic meters of sediment was displaced by this very aggressive hydraulic mining process. And just for reference, that's about a third as much as was displaced by the Mount St. Helens eruption in 1980, and about 7 times the volume that was excavated for the Panama Canal. And the sediment had to go somewhere, so it moved downstream into these V-shaped valleys and filled them up with sediment, actually created big topographic features in the landscape. For example, the Yuba Fan, which is one of the largest, is a huge accumulation of sediment along the western slope of the Sierra Nevada that is about 40 kilometers in length, 120 square kilometers in area, and has a volume of more than 250 million cubic meters of sediment. It's quite a dramatic feature, and you notice it travels all the way down to the confluence of the Feather River. The sediments didn't just build up topography like that. Some of the sediment moved all the way downstream, all the way to the Golden Gate. This upper right-hand figure shows a sediment bar that actually moved through what is now the Golden Gate and out into the Pacific Ocean. So this was a really dramatic landscape scale process. It influenced the riverbed elevations in the downstream environment such that flooding started to become more frequent and started impacting the agricultural activities that were going on in the lowland valley, as well as the steamboat operations that were really essentially moving agricultural products to market. So that led to a major lawsuit against the miners by the agricultural interests, and mining was actually ceased through a governmental decision in 1884, and further study was commissioned by this guy on the right-hand side, G.K. Gilbert, who was tasked with assessing the impacts of mining and regulating the streams that were affected by hydraulic mining. G.K. Gilbert collected a lot of data sets and developed a theory that was really important even to the present day in understanding the long-term legacy of mining. And it was basically this, that the riverbed elevation would rise and would fall again associated with the impact of mining. So it would reach some peak after the mining stopped, and then it would start to degrade again. The riverbeds would go back down. And this is called the sediment wave. It's a translatory wave that describes the accumulation and subsequent degradation of sediment in the riverbed. This process led many people to believe that by the time you reached about 1900 or even in the early 20th century, that mining sediment was completely exhausted from the Sierra Nevada system. Here's kind of how it works. This guy is standing in 1905 in the Narrows section of the Yuba. This is downstream from Englebright Dam, and you notice there's no bedrock channel there. He's standing on a big pile of sediment. And if we move forward through time, we can see that in the modern day period, the peak bed level we're quite a bit below that now. The river has cut back down into that former mining sediment surface. And notice in the near ground here, I'm actually standing when I take this picture on a big pile of sediment that was left behind when the river cut back down through that sediment. These are historical terraces that were left behind after the degradation of the riverbed. And these terraces are probably the most prominent and enduring modern legacy of the mining period. And they exist all the way along the course of the Yuba and the other drainage basins. Now, because G.K. Gilbert collected amazing data sets in the early 20th century, we can actually understand something about the evolution of the Yuba fan and other such fans in the Sierra Nevada by looking at his data and comparing it to modern day data sets. And so what we can see, for example, is if this red line represents the riverbed elevation in 1906, and the blue line represents the riverbed elevation in the Yuba in 1999. And we're basically looking at elevation versus distance along the fan, from the top of the fan all the way 40 kilometers downstream near the Feather River. And what you can notice from this is that there's a big difference between the red line and the blue line. There's about 10 meters of vertical change, vertical incision, that has occurred in the upper part of the Yuba fan and also in the lower part of the Yuba fan. And in the middle, in the Yuba gold fields, there hasn't been that much change in the elevation because there's the Daguerre Point Dam that's keeping that local base level constant. Another thing that we can see is if we look in cross-section, in the upper part of the Yuba fan, we have complete valley floor lowering that includes some erosion of terraces along the margin. Whereas in the lower part of the system, we see incision in the main channel, but we also see deposition of sediment in the floodplains. And perhaps more importantly, the rates of vertical fan incision have actually slowed down in the recent period in both the upper and the lower fan in the early 20th century, since the early 20th century. Now, why should we care about all this sediment? Well, it's because gold was really bound up within what we call auriferous Eocene gravels. These are 30 to 50 million year old sediments that contain the gravel. And in order to extract the gold from them, mercury was added to the system, as you probably all know. So it's been estimated that about 4 million kilos of mercury was lost to the mining process. And that's an issue because mercury is really high on the toxic substance priority list. And we know now that mercury is quite dangerous. In particular, California has very sensitive migratory fauna. It has a waterfowl. So California is a classic stopping location for waterfowl that are traveling on the Pacific Flyway. And it also has migratory fish populations that move from the Pacific Ocean up into the drainages of the Sierra Nevada for spawning and so forth. So it's a concern if there's mercury left over from this mining period, that could be a great concern to these ecosystems. It turns out that, in fact, mercury is in high concentrations throughout the Yuba fan. In the upper part of the system, we see very high concentrations of mercury in the parts per million range. These are about 2 orders of magnitude, or more than 100 times the background values of mercury concentrations. So this is kind of a primary tailings deposit. And as we move farther downstream, the concentrations of total mercury decrease because we get a dilution of that toxic mercury as it mixes in with cleaner sediments on its journey downstream. So modern deposits are much less contaminated with mercury, but they still have concentrations of mercury that are more than 3 times the background values. And the one I'm showing here in this right figure is actually the big sand deposit that I discovered in the lower Central Valley. So we did a full analysis of mercury concentrations throughout the Yuba fan and then farther downstream into the Feather and beyond. And we see characteristic patterns of mercury transport that lead us to believe that there's an active process that's moving mercury from the upper part of the fan to the lower fan. So we've hypothesized that there's this systematic transfer of hydraulic mining sediment containing mercury from the upper Yuba fan redistributed into the lower part of the Yuba fan. and then export of mercury-laden sediment from the lower fan into the Central Valley, into the Feather River, essentially. And the question is, what's the mechanism for this large-scale transfer of toxic mining sediment? Well, one piece of evidence is aerial photographs and satellite imagery that were taken during really big flood events like that occurred in 1997. This shows the Feather River draining from north to south and the Yuba River from east to west. And what we notice is the Yuba has a brighter color to it, indicating it's carrying a lot more sediment than the Feather River, associated with some erosion of sediment in the Yuba system and the movement of that sediment into the lower part of the Feather River. These really big floods redistribute the sediment basin-wide because they're capable of inundating the terraces, saturating the sediment, and allowing it to fail, and all of that failed mercury sediment comes downstream. And it turns out that these floods don't occur that frequently, probably on the order of once a decade. We have one of these big events that saturates the terraces, causes them to fail, and that sediment moves farther downstream. And and then the resulting pattern of mercury concentration is one where we have high concentrations in the upper part of the Yuba fan that decrease as we move downstream, but then in the lower Yuba fan we have a really wide range of mercury concentrations, including some background values that are associated with a broader zone of deposition within the Yuba floodplain. And then as we move downstream more critically, we see a high amount of mercury concentration in the lower Central Valley, indicating that mercury is actually getting there and getting deposited within the Feather River system. It's a progradation, if you will, of mining sediment into the lowland Central Valley. And we see the same thing for the Bear River as well. So most of the mercury that has been exported is actually stored in lowlands that are upstream of the San Francisco Bay Delta. So that can't be the only focus of energy here. And it manifests in this case as about a 70-kilometer long swath of contamination from the Yuba fan into the Central Valley. Now, what is going to happen in the future? Well, climate change is impacting hydrology within this region. We've seen shifts in precipitation where more of the precipitation is falling as rain instead of snow. That means faster runoff. And it also, we see atmospheric rivers, big, huge storm events that occur about once a decade along the lines of what I described. Both of these things can have an impact on the erosion of mercury-laden sediment and its delivery into the lowlands. So for example, what we see is even though the peak flood events aren't any larger in the modern period, the floods are actually getting longer. These black circles indicate higher rates, longer times to the peak discharge, and longer recession times in the hydrograph, indicating there's more time for water to seep in to the banks and terraces, allowing for failure. And essentially, when that happens, you have the potential for this erosion to occur. And that can change the overall distribution of flood events and further excavate more of the mercury-laden sediment and bring it into the lowland Central Valley. Now, why should we care about whether it's in the Yuba fan or the Central Valley? Well, it turns out that lowland floodplains are potential hotspots for the methylation of mercury, the conversion of it to its bioavailable form where it crosses cell wall boundaries and becomes part of tissues. The Sierran mercury is associated with sulfide minerals that are prone to oxidation during transport. So wetting and drying of this resident sulfate-reducing bacteria can actually methylate the mercury at the sediment-water interface at very high rates. And this is what really poses the risk to lowland ecosystems. In conclusion, I've described how the vertical incision in the Yuba fan and other fans has slowed down and has been replaced by what we call flood event-based terrace erosion. And this is really a stage of fan evolution that sustains the evacuation of this legacy sediment by floods and delivers the toxic sediment downstream into sensitive lowlands, So there are kind of corresponding risks to ecology and humans that depend on the stage of this fan evolution that's coupled to maybe an increasing distribution of extreme flood events. Just some acknowledgements of co-authors and funding sources, and I'd be happy to entertain any questions. Thanks so much.
You can see why it was worth Skyping him in. It's absolutely fabulous. We do have time for a couple questions. We have a roaming mic. All you have to do is raise that hand.
What's that? I didn't hear the question.
That's because I haven't asked it yet. Michael, this is Izzy Martin. Thank you for a great presentation. My question for you is, we keep hearing from people that there's really no reason to worry about the mercury above the dams. All of the regulatory effort should go entirely to cleaning up the mercury or addressing the mercury below the dams of California. And I wonder what you think about that.
So I'm going to try to repeat the question so I make sure that I got it right. So there's general notion that we don't need to worry about mercury that's upstream of the dams, only the mercury that's downstream of the dams?
That's right.
You got it.
That's correct?
Yes. Yeah, that's the question. What do you think?
Well, I don't think that makes much sense because basically, if you have resident bacteria that are sitting in a reservoir and the reservoir goes anoxic, right? Then you have a potential process there of mercury methylation in the reservoir. So maybe it doesn't affect the downstream ecosystems, but it is a new source, but just the discharge of that water through those dams with that new supply of methylmercury is a potential downstream risk. So I think both are relevant, but the dams do kind of fragment the problem, if you will, where there's maybe one set of solutions for what's going on in the upstream basin, and then another set of solutions or potential solutions for downstream.
Very well said. Thank you, Michael. Anybody else have a burning question out there? Yeah, back here.
Hi, this is Liz Mansfield from the Sierra Water Work Group. I had a question on your sediment wave. This may be a silly question, but I used to work in flood management in DWR, and I don't remember any discussion about how these sediment transport or wave transports may or may not affect the structural integrity of the levees along the Sacramento River and down in the Delta. Is this work, are you coordinating this in any way with the engineers of flood management?
Okay, again, I'm going to try to repeat the question just to make sure I understood it. So are people analyzing the effect of sediment transport and the filling in of channels on flood management? Was that the question?
Yeah, I know that it is a part of the equation, but it was more of the sediment waves you discussed. And how that's transported and how that fits into the equation of structural integrity and flood management.
Yeah, I think that the sediment wave I described happened quite a long time ago. And so at this point, it's more of this episodic delivery of big slugs of sediment that could potentially cause problems. So for example, I've documented in the past that you have sedimentation in these floodways that decreases the storage capacity of Sutter bypass or Yolo bypass. And that it's not lost on the people who manage those areas. Oftentimes they do some scraping of the sediment to try to reduce those changes, but there are progressive changes in the amount of water that is able to go over bank. This is particularly a problem down in Yolo bypass, and there are currently efforts and conversations about modifying Yolo bypass to account for this effect. So it is being discussed, and I have been brought into that conversation somewhat to talk about the sediment component.
Thanks, Michael. Michelle Wood, would you like to ask your question? And we'll really call this the last question. She always has such good questions. All right, Michael, this is our last question.
Okay.
Have you tried to estimate the volume of contaminated material in the fan, and how long would it take these episodic terrace failures and erosion events to remove that?
Yeah, great questions. So yes, we have been trying to estimate the volume. So we've been doing some deep coring throughout the Yuba fan and trying to document the concentrations at different levels and also the toxicity of that mercury, because not all mercury is necessarily dangerous. Some of it could be bound up in sediments and is not really available to the bacteria for methylation. But then again, we're trying to get an overall volumetric control on how much mercury is there. And the second part of the question is that we made an estimate in the paper that was about more than 10,000 years to evacuate all this contamination. And that was really based on a back of the envelope calculation of how much sediment moves during one of these decades and one of these floods occurring once a decade, and then extrapolating that to the total volume of sediment stored. But of course, it's not quite that simple, because as the river widens progressively, you need a larger and larger flood event to erode a terrace. So it's a fairly complex problem, but let's just say for our lifetimes, there's a lot of sediment and a lot of it is in play when it comes to big floods.
Thank you so much, Michael Singer, for taking the time to be here today. We really appreciate it.
Thank you. Thank you for having me.
And goodbye for now.
Thank you.
Thank you.
Enjoy the conference, Amber.
All right, so I'm going to introduce our next speaker. Bye, Michael.